Okay, let's try to start our sponsor talks. I know it's going to be somewhat difficult with the slight delay in our last session, but we need to keep to our schedule. We have a tight end of today. So without further delays, let me welcome James from Meta for this Meta sponsor talk. Thank you, James. If we will have time for 1 or 2 questions after the talk.
Yeah.
Okay, so James, thanks.
Hi everyone, my name is James Zheng. I'm work at Meta AI networking team. Very happy to have this opportunity here to share our networks for our large GPU cluster. At Meta, we have been consistently building larger and larger GPU clusters. Specifically, the scale that we are working with has grown exponentially in the past few years. Before 2023, the vast majority of Meta's ML workload uses fewer than a couple of hundreds of GPUs. In 2023, we start building clusters that have thousands of GPUs. We have shared that Llama 3 was running on 2 24K clusters. Last year in 2024, for Llama 4, we have been building over 100,000 GPU, regional scale cluster that goes over multiple data center buildings. For Llama 5 and beyond, we projected that this number will go over 1 million soon. Note that this is not the entire GPU fleet. There are even more GPUs and other accelerators to support non-Gen AI machine learning workloads, such as recommendation models. Meta is not alone in this field. Google, Microsoft, Amazon are going into an arms race of CapEx spending. This trend is only going to accelerate in the next few years. The networking community, that is us, is in a unique position for this AI infra revolution. In some sense, we are back to the focal point or the narrow waist between hardware and software. Below us, network is the connecting tissue to bring different accelerators in different geolocations together so that they can work as one giant server. On top of us, model developers rely on us, the abstraction provided by us, so that they can write scalable software to leverage this expensive hardware. In this talk, I will go over the network architecture evolution of Meta's Gen AI clusters. Then I will dive into the software portion of it, specifically the communication library. So it all starts with a very simple building block, what we call AI zone. An AI zone is a 2-stage cross topology. The RTSW, or rack training switch, acts as a leaf switch, connecting 2 GPU hosts within an AI rack. The RTSW can be installed in the same rack as the GPUs, in which case it connects the GPUs using direct attached copper cable. Or it can be installed in its own end-of-row rack, in which case it connects to the GPUs using optical transceivers. The CTSW, or cluster training switch, provides connectivity between all the AI racks in the zone. It is installed in MDF. Each RTSW uplinks to a group of CTSWs using single-mode fiber and 400 gig optics. This network is intentionally undersubscribed to allow some buffer for maintenance of potential failures, ensuring robust and reliable operation. The AI zone occupies part of a data center building, and one data center building can have multiple AI zones. Let's make a closer look at the structure of a type 1 data center to help understand how AI zone can be deployed in it. So this is our standard Meta data center, originally designed to support regular OCP server racks. In general, we have 4 large server rooms or data halls. Each data hall can accommodate 2 AI zones for a total of 8 AI zones in a given data center type 1. The MDFs serve as a first network aggregation point for server racks in the data hall. The BDF contains the core of the DC fabric. With this brief introduction about Meta's data center layout and the AI zone building block, we can dive into Llama 3 scale DC network design. We start with what we call a 24K cluster. We built this cluster in 2023 specifically for Llama 3 training. As we see in this drawing, the network occupies the entire data center building with 4 data halls. We really wanted to pack as many GPUs in one DC as we could, so we removed all the non-AI servers from that DC and deployed 2 AI zones per data hall. It resulted in 8 AI zones in one building. Now we need to connect these 8 AI zones together. For that purpose, we install a super spine layer in the BDF, which we call ATSW, or Aggregation Training Switch Layer. This aggregation tier resulted in 24,000 interconnected GPUs. While 24,000 clusters serve its purpose for Llama 3, next generation model demanded even bigger GPU scale. This brings us to the 100,000 cluster. This is the 100,000 cluster. And the first thing we notice is that instead of just one building, it's now multi-building. The network is built on a type 1 region comprising 5 buildings. Each type 1 region, each building houses 4 data halls, bringing in a total of 20 data halls across the region. As you can see in this picture, DC 2, 3, and 4 are fully populated with 8 AI zones each. Building 1, however, has only 6 AI zones, with 1 data hall dedicated to supporting services, examples like storage servers that feed the data into the GPUs. In total, there are 38 AI zones housing over 100,000 GPUs across the entire region. This makes it one of the largest AI clusters in the world. Now let's get a closer look to the network topology per building. Here we zoom into one single building topology, and we can see 4 data halls, 2 AI zones per data halls. Each AI zone is exactly what has shown earlier. It's a 2-stage cross topology. Each layer and each and every CTSW in the data center uplinks to a core layer of 76 ATSWs. These ATSW layers play 2 roles. One, it interconnects the 8 AI zones within the building, and second, it connects this building to other buildings in the region, providing regional connectivity. This also was mentioning that for one AI zone to cross the ATSW layer and talk to another remote zone, there will be oversubscription of roughly 3 to 1. Next, let's take a closer look at the ATSW layer. This is the regional network. It's constructed by a fully meshed ATSWs that share the same index from all 5 buildings. For example, all the ATSW1s from all 5 buildings form a mesh, all the ATSW2 from all the 5 buildings form a mesh, etc. This creates 76 distinct orthogonal planes representing the in this drawing in purple. Within each one of these planes, the ATSW uses 144 uplinks evenly distributed across the other 4 remote ATSWs in the plane, with 36 uplinks each. These are white lines we see in the illustration. It's worth mentioning that the fiber infrastructure between these buildings are based on what we call OSP, or outside plant fibers. The end-to-end physical distance between these ATSWs, it's already 3 kilometers away. So what's next? You probably saw Zach has announced that our next milestone is Prometheus. It's a super cluster which we currently under construction. Prometheus will span an entire metropolitan area, connecting multiple sub-regions. In the future, we can also expect that GPU and accelerators scale may be in the hundreds of thousands range, or even cross 1 million. We are sure that these new and exciting challenges will emerge from the larger network diameters. Number one, we need to train models over very long distances, potentially hundreds of kilometers away. And then the training may be needed across a diverse set of data center types and heterogeneous accelerator models, NICs, and switching platforms, across subregions. Now, let's dive into the communication library side of the generative AI cluster. From Llama 3 to Llama 4, our model complexity has changed a lot. The number of parameters obviously increases, but the model training now uses 4 to 5 different parallelisms at different layers. The model is also natively multimodal, which puts a lot more burden on the wire. We just discussed the multi-layer networking architecture. While it does the job of connecting many GPUs together, the latency poses a very big challenge. For example, the latency on different racks, even within the same AI zone, is 7x more latency. If we cross AI zones, we are talking about 15x to 30x of latency. From software side, we needed to overcome, or more accurately, hide this latency by mapping the right parallelisms to a network topology. Each parallelism, fortunately, has its own characteristics. Data parallelisms, for example, has low bandwidth and can tolerate high latency, so we can use interzone network. Pipeline parallelism uses medium bandwidth and predictable latency, so we can map it to interzone. Expert parallelisms and tensor parallelisms are both very demanding. We map them in the in-zone network or even in the same scale-up domain. Once we map these parallelisms to a right network, we need to optimize the communication within the parallelism. We have developed a Meta in-house custom transport stack to fulfill our needs, which is illustrated in purple. It contains Nickel X, which is a fork of Nickel, as well as a custom layer called Citron. Our stack sits between PyTorch and Rocky transport. It has several components, from the top to down. Nickel user-facing API. This is just a regular Nickel API. And then we have host-driven algorithms. This layer implements the core collective communication algorithms, while GPU is the primary compute engine. We use CPU for orchestration. Beneath it is the zero-copy-based algorithm, transport mapping. This layer is crucial to achieve high performance by minimizing data copies, which I will talk about later. And finally, the transport. That's RDMA, NVLink. This is provided by Nickel stack. Nickel of course, supports various high-speed interconnects. For the sake of time, I will only cover one key feature of Citron, zero copy. So why do we need zero copy? There are two reasons. First, resource contention and efficiency. When Nickel performs a collective core, you will need to perform 2 additional copies under the hood. Data has to be copied from the compute buffer from Nickel to Nickel internal channel buffer before the data gets sent over the wires. On the receiver side, it will get through the same path again, get copy again. While this simplifies the end-user responsibility by lifting the explicit buffer restriction, this leads to resource contention with other kernels that heavily use SMs, and that's not very efficient for large-scale model training. The second reason is inflexible network performance tuning. The size of the message that can be posted into the network is directly constrained by the capacity of the channel buffer, which is part of Nickel. However, finding the optimum this buffer size is very hard. If the buffer is too big, it may seem like it's easier to saturate the network bandwidth, but the copy takes more time. If the buffer If the buffer we chose is too small, then it's easier to hide the data I/O within the computation time. However, this comes as a cost of the network transfer speed, especially for high latency networks, such as the one that connects different AI zones. Smaller buffers can slow down the data transfer a lot. To address this limitation, we re-architect the parts of the communication library. We implemented user buffer restriction in the collective library to support zero copy. This means that the source NIC can directly read the data from the source compute buffer in order to perform the RDMA transaction without needing an additional copy to a channel buffer. To do this, we need smooth user buffer restriction. We have developed transparent user buffer restriction for PyTorch cache allocator all the way to CTran, from PyTorch all the way to CTran and NicoX. We have developed memory pool approach to control the amount of the restriction when the buffer reuse is low. Zero copy enables flexible network performance tuning based on the network topology. Since now it exposes the entire user message, we know how long the message is. We now have much finer control over the network usage. There are many other tricks that we have leveraged during this 100K pre-training, including all-gather algorithm built for various patterns, fault-tolerant or reduced for elastic data parallelism, the SM3 point-to-point communication for pipeline parallelism, the SM3 one-sided put for tensor parallelisms for better communication computation overlap. We are open sourcing CTran very soon, and we will share more details later. So there are some takeaways I hope you will have after listening to this talk. First, modern Gen AI workload demands larger and larger cluster. And this trend is only accelerating. State-of-the-art Gen AI cluster now covers the entire data center region with up to 100,000 GPUs. And we hope it will cross 1 million soon. Networking software stack is also evolving very quickly with these hardware and models. And networking is the focal point of the AI infrastructure, which I hope all of us should be very excited about. So that concludes my talk. Thank you very much. I'm happy to take questions.
Thank you very much for the great talk. One question, what do you see the future directions of network design, topology, architecture to support Gen AI and AI training in the future? Thank you.
Good question. I think the network design used to be, the regular data center networking design is usually very utility-like, right? We build a utility, we build a fatter pipe, and we over-provision everything, and it will accommodate multiple workloads. In the future, I think we will see more and more data center design that is tailored to a specific workload, which is AI workload. And in fact, there are some specific AI networking design is just tailored for a specific AI workload, which is Gen AI training. And that trend is only to continue if we keep investing in the generative AI space. So I would expect that I will see more hardware software co-design in the future.